So for the last half of chapter 7, still focusing on solutions, the concentration is defined as the amount of solute dissolved in a certain amount of solution. So I think we're familiar with that when we are focusing on like how concentrated the acid is or something like that. Well, when you're asking how concentrated it is, what you're really wondering is how much solute is in that solution. So 4 of the concentration units we're going to work on in this particular chapter are 3 of them are percents. A percent mass volume, a mass percent, a volume percent, and then we're going to deal with molarity. So taking the first one, the mass volume percent, has this formula where you take the grams of your solute, divide it by the milliliters of solution, and then you're going to multiply it by 100. So that's all you need to do. And the math is going to be pretty simple. We're just going to tell you how much solute you have and how much solution you have, and you just have to plug it into the formula. So make sure you go to your information sheet because we have all of these formulas for these 4 concentration units on there. So here is an example. What is the percent mass volume of a solution made by dissolving 5 kilograms of potassium iodide in enough water to give a final volume of 250 milliliters? Write your answer to 2 numbers past the decimal. So why don't you go ahead and pause this video and see if you can get that previous formula and plug it all in correctly. Okay, so our formula says the percent mass volume is equal to the grams of the solute. And in this case, if I read the problem, the solute is always going to be given to you with, molecular formula. So it's the grams of the potassium iodide over, and the formula wants grams of the milliliters of the solution. Solution is abbreviated SOLN. So if we just plug, and we can't forget we have to times it by 100 to turn it into a percent. So the grams of potassium iodide is 5. And the volume of the solution in milliliters, and then times it by 100. So you have to be careful. Don't ever plug anything into this formula unless you're in grams and in milliliters. So if the problem gives you the volume in liters, you first have to convert it to milliliters before you plug it in here. So when you type this into your calculator, you're going to end up getting 0.20%, and you have to let the reader know what kind of percent. And this particular one is a mass over volume percent. The other 2% is volume percent, and in that one you take the milliliters of solute and put it over milliliters of solution times 100. If we want a mass percent, then it's the grams of solute over the grams of solution. Okay, something to be wary about, or careful about, is that it's the solution that goes on the bottom. So if you ever come by a homework problem where they give you the grams of solute and the grams of solvent, you need to remember that the solution is the solute plus the solvent. So you'd have to add both those together to get the total mass of the solution. So here is a picture showing making the mass percent solution. So they start off by weighing out 8 grams of potassium chloride. So if you look at the scale, it says 8 grams. They put it in there, and then they start adding water. And they're adding water, and they're watching the scale the whole time until it gets up to 50 milliliters. So what they've done is they've added 8 grams of the solute, and they've added enough water till the mass of the solution was 50 grams. So my question to you then is, what is the percent mass of this new solution that they've made? Well, the first thing you're going to do is you're going to go get the formula, and it tells you the percent mass is the grams of solute, which you think about what is the solute in this problem. Well, what is it they weighed out? They weighed out the potassium chloride, and you're going to put that over the grams of the solution, and you're going to times it by 100. So if we plug our numbers in, we have 8 grams of the potassium chloride, and we are going to divide that by a total of 50 grams of the solution, times it by 100, and we get 0.16%, and we have to let the reader know what kind of percent. It's a mass percent. All right, then the last one is molarity. This is the one that chemists use quite often. Now, it's defined as this first equation, where molarity is the moles of solute over liters of solution. Notice that it is liters instead of milliliters. The other three formulas called for milliliters in the denominator. This one you need to make sure you're in liters of solution before you plug it in. So you're going to put the moles of your solute over the liters of solution. Sometimes the problem tells you how many grams of the solute you had. So that if we give you grams of solute, you're going to go get this formula right here. So the tricky part about using this formula is that it calls for the molar mass of the solute. So you're also going to have to go to the periodic table and add up the molar mass of whatever your solute is and put that in here. A common mistake that I see students doing is they don't realize that the molar mass, the product of the molar mass and the liters goes in the denominator. Okay, so don't forget that. Both of these are on your information sheet. So when the question is asking you for molarity, you need to decide which one of these formulas to use. And it's as simple as, if you're given moles, use the first formula. If you're given grams, use the second formula. So here is an example. What is the molarity of a solution made by mixing 23 grams of sodium hydroxide in enough water to give 50 milliliters of solution? So first of all, my first question to you is go back to the previous slide and pick which formula you're going to use. Since they're giving us grams of solute, I recommend using the formula where molarity is the grams of the solute divided by the molar mass times liters of the solution. So when we plug everything in, we have got 23 grams of the solute, which is sodium hydroxide. You go to the periodic table, and sodium's about 23, oxygen's 16, hydrogen's about 1, so approximately 40 grams is the molar mass of sodium hydroxide. And we're going to multiply that by, now it has to be in liters, and I can see that the information here is in 500 milliliters. So the first thing I really need to do is take that 500 milliliters and convert that into liters. So there is 1,000 milliliters in 1 liter. So that's going to end up telling 0.500 liters. So that's what I'm going to put in the denominator down here, is the half of a liter. And molar mass, I made a mistake. Molar mass is supposed to be grams per mole. So when you type this out, what happens is you have a fraction within a fraction. So if you remember how you deal with that is you invert and multiply. So this grams over moles is going to end up getting flipped over, and the grams will be in the denominator and the moles in the numerator. So the grams are going to cancel, and your unit is going to end up being a mole over a liter, which is the perfect unit for molarity. So when you type this out, you end up getting 1.15 moles over liter. So you can either write it like I have on the slide with moles over liter, or you can use capital M. It means the same thing. So capital M is moles per liter. Okay, so those are the 4 concentration units. We're now going to talk about how you do a dilution. So instead of starting from scratch like we did in the previous examples, it's often easier and faster to make a solution by diluting a more concentrated one. So for example, if I'm a scientist and I'm going to go do an experiment and I need to use a liter of this acid that I want to be, 5 molar, this 5 molarity acid. And instead of starting from scratch, what I'm going to do is I'm going to go into my chemical stockroom and I'm going to see if I'm lucky, I've got one that's 5 molarity. But if I don't, I'm going to look to see if I've got something more concentrated. So if I can find a bottle of that acid that's more concentrated, I'm just going to grab that and add some water and dilute it until I get to the 5 molarity that I need. So doing a dilution is much quicker than having to go weigh out the solute and dissolve it and things like that. So in a dilution, you're always going to take a concentrated and add water to it. Because you're adding water, the volume is going to increase, and then the concentration is decreasing because you're diluting it. So if we look at these 2 pictures, we're starting off with something that's kind of a darker red, very concentrated. They're trying to show that by having a lot of the solute dots here. And then we add water to it, and notice the color is getting lighter because we're diluting it, we're adding water. And the particles are not as concentrated. So volume is going to increase, but the concentration of your solute particles decreases. So for any dilution problem, the following formula applies. So this is the dilution formula. I have this on your information sheet for you. So when you're reading the problem, once you identify that the problem is wanting you to do a dilution, go get this formula from your information sheet. So note when you use this formula, the concentrations can be in any unit. It can be a percent mass, a percent volume, molarity, doesn't matter as long as both concentrations are the same unit. Same thing with your volumes. It can be milliliters, liters, quarts. It doesn't matter as long as they're in the same unit. So here's an example. So what if the new concentration, what is the new concentration when 50 milliliters of a 10% sucrose solution is diluted to 100 milliliters? So I have 50 milliliters and it's 10% and I dilute it to 100 milliliters. So I double the volume. So your common sense is going to tell you, well, if I double the volume, then I'm going to half my concentration and it's only going to be 5% now instead of 10%. But how would we set that up using our dilution formula? So you first write down the dilution formula and then you plug in the numbers you know. The concentration of the concentrated one was 10%. And I started off with 50 milliliters of this 10%. And then I added enough water till I diluted it to 100 milliliters. And so what I'm looking for is what is my new concentration. So I just have to algebraically solve this for my C dilute. So I take the 10% divided by, or times it by the 50 milliliters, divide by 100. And so my milliliters are going to cancel. And my unit is going to come out in percent. So here is another dilution example. So how could you prepare 250 milliliters of a 2.5 molarity sulfuric acid solution, starting with an 18 molarity sulfuric acid solution? So I have, first of all, can you see which one is more concentrated? Is the 18 molarity more concentrated or less concentrated than the 2.5 molarity? And I hope you can see that the bigger the number, the more concentrated it is. So how can you prepare 250 milliliters of 2.5 if I start with 18 molarity? So we need to do a dilution, and we're going to dilute the concentrated solution with water. But the question is, how much water am I going to add in, and how much of the concentrated solution am I going to start with? So let's go ahead and set this up. So the first thing we want to ask ourselves is, I've got my 18 molarity solution, but I need to know how much to pour out, and then I'll add water to that. So the first thing I'm going to ask myself is, what is the volume of that concentrated solution do I need? So I rearrange my formula, solve for volume concentrated, and then I just plug in my numbers. The concentration of the diluted one was 2.5 molarity. The volume after I diluted it was 250 milliliters, and the original concentration of the concentrated was 18 molar. When you type that into your calculator, you figure out that what you need to do is you need to take 35 milliliters of the concentrated stuff. So you pour that out, you've got 35 milliliters here. Now you're going to add enough water until you get up to this final volume, this 250 milliliters that we wanted. So next you mix the 35 milliliters with water until the total volume is 250 milliliters. I took a copy of your information sheet because I wanted to make sure you could locate where those formulas are. So here are all the formulas we've discussed today. Notice that here's your 2 molarity ones. So this is an or right here. You can either, if I'm asking you to calculate molarity, if I give you moles, you'll use this formula. If I give you grams, you'll use this formula. And here's your dilution formula that we just used. Electrolytes are compounds that separate into ions when you dissolve them in water. The electrolyte is considered to be a strong electrolyte if the substance completely dissociates. It completely ionizes. So it breaks apart, you get a lot of ions. A solution containing a strong electrolyte is going to conduct electricity really well. Weak electrolytes are substances which ionize in water much less than 100%, so they don't 100% break apart. A solution containing a weak electrolyte is going to conduct electricity, but very poorly. Non-electrolytes are substances that do not dissociate or ionize in water. Their solutions do not conduct electricity. So they might dissolve in water, like sugar will dissolve, but it doesn't conduct electricity. Focusing a little bit on strong electrolytes. Water-soluble ionic salts or solids. So up to this point, what I had told you is that most ionic compounds are soluble in water. And so you're not going to know. If this was an upper level chemistry class, we teach students how to, which ones to memorize are soluble in water and which ones aren't. So you're not going to know that up to this point. So if I give you an ionic compound, you're just going to assume that it is soluble in water. And if it's a strong electrolyte, it is going to break up 100% into the ions. Notice that I have a arrow pointing completely to the right. That is one of the indications that it is a strong electrolyte. 100% of it went to the right and broke up into ions. So your water-soluble ionic solids are strong electrolytes. Your strong acids and your strong bases are also strong electrolytes. So we're going to talk about this in the next chapter, your acids and bases. But I'm going to be telling you next chapter that your strong acids are those that are also strong electrolytes. So hydrochloric acid here, one arrow to the right, meaning it's going to totally break up into ions. Same thing with your bases. 100% to the right, so you get 100% of these ions. You're not left with any of the stuff that's on the left. Weak electrolytes, on the other hand, are going to reach an equilibrium condition. And the dissociation then must be written with the double-headed arrow, the arrow representing that you're at equilibrium. So weak acids like acetic acid or phosphoric acid. This here is an equation showing acetic acid in water, and I'm showing you that not even 0.5% of these acetic acid molecules are going to break up into ions. So it's a very small percent that turn into ions. So it's a weak electrolyte. It's going to conduct electricity very weakly. So to conduct electricity, you need to have a lot of positive charges floating around in the solution so it can carry the current. If you have a weak electrolyte, there's not very many positive and negative charges, so the current is very weak. So just make sure if you're using a weak electrolyte, make sure you have that double-headed arrow. A weak base, an example of that would be ammonia. So if you put ammonia in water, similar to acetic acid, you get less than 0.5 of your percent that's going to break up into ions. So if I have a beaker with ammonia, I am going to have a little bit of this ammonium ion and hydroxide ion, but the majority of the molecule I have in here is just the ammonia that hasn't broken up into any ions. Same thing with my acetic acid. If I have a beaker of acetic acid, I'm going to mainly have neutral acetic acid molecules, but I'm also going to have a small amount of these ions. Non-electrolytes are substances which do not dissociate in water. Their solutions do not conduct electricity. Those are going to be hard for you to be able to spot. So basically I'm going to kind of stick to sugars for starters. So if I tell you you're putting a sugar in water, go ahead and memorize that that's a non-electrolyte. And alcohols, we'll talk about those more when we get to a later chapter. So solutes and ionic charge. So in water, the strong electrolytes produce ions, therefore they conduct electrical currents. Your weak electrolytes produce few ions, and your non-electrolytes don't produce any ions. So here's a picture where they've taken sodium chloride and they've just put it in this beaker and they've dissolved it in water. And then they put in a light bulb that has the electrodes submerged into the water. And then they plug it in or they hook it up to a battery, something that's going to start a current. Well, in order for you to continue to have a current, you need to have some ions in this solution that'll carry that current from one electrode to the other electrode. So they're showing you that if you did this experiment, the light bulb would glow brightly because the electrical current would be carried through that light bulb. If I submerge the light bulb's 2 electrodes into hydrofluoric acid, which is a weak electrolyte. So notice here with my weak electrolyte, most of my hydrogen fluoride molecules are still just neutral molecules, and only a few of those have broken up into ions. If I go back to my sodium chloride, notice 100% of them have broken up. That's their definition of a strong electrolyte. So this one will make the light bulb glow just slightly because it's weakly carrying the current. And sugar molecules don't have any charge. They'll dissolve, but they don't make any cations or anions, so the light bulb doesn't come on at all. Electrolyte equivalent concentration. So sometimes and often when you're working with biochemistry and reactions or reactions or concentrations in the body, what somebody's going to be interested in is what is the concentration of charge, not necessarily concerned with the concentration of the solute particles, but they want to know how much charge do I have in a solution. So electrolyte concentrations are often reported using a concentration unit called milliequivalences per liter. So here is the unit. So those of you going into nursing, you might see a solution that has this number following a unit, and what they're focusing on is how much charge. So milliequivalences per unit. It turns out that 1 equivalent is equal to 1 mole of charge. So if I have a mole of sodium, I'm going to have 1 equivalent of charge. 1 mole of calcium, since I have a 2 plus here, is going to have 2 equivalences of charge. So for every 1 mole of calcium, I get 2 charges that come along with that. Chloride, 1 mole of chloride ion is going to give me 1 equivalent. So notice they don't necessarily state whether it's a positive charge or a negative charge. It just is an equivalent, whether it's positive or negative. The phosphate ion here, since it has a 3- charge, we get 3 equivalences per every 1 mole of the phosphate. So you're going to end up needing to use these ratios as conversion factors and to set up factor label problems with them. And the tricky part is that I don't give you these. You can look at an ion and be able to come up with the conversion factor all on your own just by looking at the charge. So always make sure you put 1 mole of your ion on one side of the ratio, and on the other side you just put down whatever the charge is, followed by the word equivalent. So here's an example. How many equivalents? So the question is asking for how many equivalences are in 1.75 moles of my aluminum ion. Now, if this question had said how many equivalences in 1 mole of aluminum ion, we'd say 3. But we don't have 1 mole, we've got 1.75 moles. So I am going to try to convert my moles of my aluminum ion into equivalences, because that's what the question is wanting, is how many equivalences. Well, if I have 1 mole of aluminum ion, how many equivalences are there? So you just look at the charge of aluminum, which is 3. And so you just say 3 times the 1.75 would give us, so my moles of aluminum cancel. So we have 5.25 equivalences is equal to my 1.75 moles of aluminum ion. So electrolytes are extremely important in biological systems. They permit proper nerve impulse transmissions. They promote or permit proper muscle contractions, proper function of all your cell membranes, and the list goes on and on. So in the body, your electrolytes are very important. In a given fluid, the number of positive charge better equal the amount of negative charges. So the milliequivalences of positive charge have to equal the milliequivalences of negative charge in any solution that's in your body. So here's an example focusing on the fluid on the outside of the cell versus the fluid on the inside of the cell. So extracellular is on the outside, intracellular is the fluid on the inside. So picking apart the fluid on the outside, it appears that there's sodium, potassium, calcium, and magnesium are the ions on the outside of the cations on the outside of the cell. Mixed in with those, we have these anions floating around in the solution on the outside of the cell. If you add up the equivalences of each of these, it looks like most of the charge is coming from your sodium cation, but you add up all the equivalences of positive charge and you get 155 milliequivalences per liter of positive charge. So if you add up your anions, you better end up with 155 milliequivalences of negative charge. Inside the cell, there's 202 milliequivalences per liter of positive charge, and there's 202 milliequivalences of negative charge. So